Most ONNX reranker exports are fast until you measure batching, tokenization, and dynamic axes. This is the workflow you'll learn to export the reranker and re-rank a small list for a query, so you get faster results. You will export and run a fast, stable reranker. I'm Professor Pi, teaching search and IR with simple Python. Exporting a reranker to ONNX Runtime solves a common production problem. Training or prototyping a neural reranker in PyTorch is easy and accurate. Running that same model in a live service can be slow or inconsistent if you keep the full framework. Success means the model returns the same top choices, but with lower CPU time per query and predictable batching behavior. Think of this as taking a refined scorer and turning it into a compact, repeatable black box. ONNX Runtime runs the graph with fewer framework overheads. Quantization can shrink weights and speed up CPU inference without rewriting your model logic. The payoff is lower latency for tight user-facing loops or more queries per server. At a high level, we will score a query against a few candidate passages with a Cross-Encoder. Export that encoder to ONNX with a fixed sequence length. Run the ONNX model to confirm parity. Quantize the ONNX file to make it smaller and faster. And finally, plug that quantized reranker into a two-stage pipeline, so only a short list is rescored. This short demo uses a tiny toy corpus, so you can see each step clearly. We keep the max token length fixed to avoid dynamic axes complexity. That makes the exported graph simpler and the runtime shapes stable. Now we will load and score a query with the original reranker. This snippet loads a sentence transformer's Cross-Encoder and uses it to score a query against a few candidate documents. The variable q holds the query text, and docs is a small list of passages we want to re-rank. The object CE is a Cross-Encoder loaded with the MS Marco Mini LM model, which scores relevance for text pairs via the Cross-Encoder predict method. The list comprehension builds the query document pairs in the format the Cross-Encoder expects. The array S contains the floating point relevance scores for each pair, and NumPy's argmax finds the index I of the best match. The printed top document shows the baseline PyTorch re-ranking result, which sets a reference for later ONNX speedups. Next, we will export the Cross-Encoder into an ONNX graph with a fixed input shape. This example converts the loaded sentence transformer's Cross-Encoder into an ONNX model using the torch.onnx export function. The variable mx is a fixed maximum sequence length chosen to keep export simple and reproducible. The tokenizer call x builds example input tensors for a single query document pair, matching the shapes the model expects at inference time. The torch.onnx export function traces the Cross-Encoder model with those tensors and writes the ONNX graph to a file named ce.onnx. Fixed shape export is straightforward and fast, and you will use the same max length at inference to match the graph. The printed path confirms that the ONNX model was created and where it lives. Now we will run the ONNX graph and compare its top choice to the PyTorch baseline. This code runs the exported model with ONNX Runtime and checks ranking parity versus the original Cross-Encoder. The variable ses is an ONNX Runtime inference session created from the ce.onnx graph with the CPU execution provider. The tokenizer prepares batched query document inputs as numpy arrays using the same max length mx used at export, so shapes align. The call sesRun returns logits for each pair, and Ravel flattens them into a single one-dimensional array. The index I2 of the largest ONNX logit is compared to the index I from the original predict run to create OK, a simple parity flag. If parity is true, your ONNX model preserves the top choice, validating ranking stability. Next, we make the ONNX graph smaller and often faster by applying dynamic quantization. This snippet uses ONNX Runtime, Quantization, Quantize Dynamic, to reduce model size and unlock faster CPU execution. The variable QPath is the destination for the quantized ONNX graph. The function QuantizeDynamic reads the original ce.onnx and rewrites weight matrices in lower precision, typically int 8, while keeping activations in higher precision at runtime. The variables R and the printed size ratio report the new size divided by the original size, rounded to 2 decimals. Lower ratios indicate a more compact model. Increasing quantization aggressiveness can improve latency on CPU, but may nudge scores slightly. Dynamic quantization usually keeps ranking stable for cross-encoders. Finally, we plug the quantized reranker into a 2-stage flow, where a cheap filter limits candidates. This example simulates a practical 2-stage pipeline, where a coarse signal feeds a faster reranker in ONNX Runtime. The variable base is a toy proxy for a lexical retriever score, counting pizza overlaps and a small length prior. The array IDX selects the top 2 candidates to keep rerank costs low. The tokenizer builds paired inputs only for those candidates, matching the fixed MX length. The QSES inference session on the quantized model computes rare, the ONNX logits for the short list. The index best picks the final winner among candidates. The printed final top shows the re-ranked choice, demonstrating lower latency and stable quality at the last hop. In a real system, swap the toy lexical signal for your current retriever and increase the shortlist to match product constraints. The same fixed length and quantized graph will speed repeated calls and make benching easier. Recap: it exports a neural reranker to a stable ONNX graph, preserving top choices. Use it when you need predictable, lower latency CPU inference for a re-ranking hop. Caveat: fixed input shape and quantization choices can nudge scores, so validate ranking parity on your data. Next step: measure end-to-end latency on a larger candidate set and add timing and accuracy checks so you know the real production improvement. If short, practical IR helps, subscribe and watch the IR videos.